Hello there, let's do IP version 6. Now the cool thing is you don't need to worry too much about IP version 6 for your A+ exams. You might get a question, at most 2, usually asking you to recognize what an IP version 6 address looks like, and maybe a couple questions about it. Now first up, why do we have to have IP version 6? Why can't we just stick with IP version 4? So let's compare the two and see why. So first up, with IP version 4, what you're looking at is a 32 binary bit address. Now with 32 binary bits, that gives us about 4.3 billion IPv4 addresses. The problem is, 4.3 billion addresses is not that much. Just for you to be watching this video right now, there are loads of IP addresses in YouTube's data center. Add to that all of the IP addresses used by the various internet service providers and internet exchange providers just to get the packets to you so that you can see them. So a lot of IP addresses get used up even by a single person going online and doing something. Admittedly, not exclusively used up by you, but a lot more addresses get used than you think. Then, with IP version 6, you have a 128 binary bit address. So the address is 4 times longer. But because we've got 4 times more combinations of 1s and 0s we can pull off, we have 340 undecillion addresses, which sounds like a made-up word. So to give you a bit more context, that is 340 trillion addresses. That's quite a lot of addresses. Now in terms of usage, IP version 4's addresses are mostly used up now. Although we do have some things that make life easier, like the private addresses we spoke about previously, we do have limits, and we have hit them / are hitting them depending on who you listen to. Whereas with IP version 6, there's plenty of addresses to work with, and the addresses are only being made available in a very conservative manner. The idea is only once a certain block of IP addresses has been used up, will another block of V6 addresses be made available. In other words, we're learning lessons that we should have learned long ago about issuing and giving out public IP addresses. And then, you've also got a very badly designed header on IP version 4, at least by modern standards. Whereas IP version 6 has a much more simplified packet header structure, which makes it more efficient for routing despite the addresses being much longer. And there are a couple of other extra benefits that you don't need to worry about, at least at this level. So the short takeaway here is you've got more addresses and a better designed packet header for routing. That's why you want V6 addresses. Or at least that's why the world needs V6 addresses. The problem though is the format, I think. Once you've wrapped your head around IP version 4, it feels like a lot of time and effort went into that, and you don't really want to give up on that work you've put in. And then you see the IP version 6 address format, which is being 128 binary bits, getting divided into 8 segments of 16 bits that are separated by a colon. It gets quite difficult. And the problem is, we don't write it in decimal, because it's simply not viable. Each of those 8 segments would possibly range between 0 and 65,535. So instead, we're using hexadecimal. And an IPv6 address can look something like this. And that is why I believe that people do not like IP version 6, well, part of the reason at the very least, is the address is really long, complicated, and difficult to read and remember. But it is a really decent address. Now the address can be written in a shorter format. So let's see what that can look like without getting too confused and possibly mistaking an IPv6 address for something else. So first of all, the idea of address shortening was made to create the early adoption easier by making the IPv6 addresses shorter to type and shorter to remember. And there are 2 steps that we have in shortening. The first one is that we can drop leading zeros from a segment. And the second thing we can do is we can replace consecutive segments of zeros with a double colon. But you can only do that once. So let's see what that looks like. If we take that address we had earlier, 2001, 0db8, 0000, 0000, 0008, 0800200200C417A. Just flows off the tongue, right? We can apply that rule of dropping leading zeros. Now, just to clarify what we mean by a leading zero. If I take an amount of money, like $900, those zeros that come after the 9, those are called trailing zeros and they hold value. You don't need mathematics to turn $900 into $9. I can definitely do that myself without the need of mathematical tricks. If we have an amount like $901, that's a middle or a middling zero, and it also holds value. I don't need to drop zeros to turn 901 into $91. But if I write an amount of money like this, $009, that is leading zeros. Those leading zeros hold no value, therefore they can be dropped. So if we run through this, we've got a leading zero there. We've got 3 leading zeros in that field, because whether you write 1, 4, or a million zeros, 0 is 0. Same for that next segment, also a bunch of zeros. For the next one, it's 3 zeros and then an 8. We can drop those. We can also drop that 0, but not the zeros that come after the 8 in that segment. And then, just like the 2001, I can't drop those middle zeros of 200C. And that will shorten the address to look like this. 2001 colon db8 colon 0 colon 0 colon 8 colon 800 colon 200C colon 417A. So it's much shorter. But remember, there's that second thing we can do, which is to replace the consecutive segments of zeros with a double colon, but once only. And there is our consecutive segments of zeros, where instead of writing colon 0 colon 0, I can just rewrite it as colon colon. Now, in this example, it didn't save us that much typing, but in IPv6 addresses where there are loads more zeros, we can expect to see a lot more space being saved by the double colon. So seeing an IPv6 address that has less than 32 hexadecimal characters is okay, as long as it's leading zeros that have been dropped, and seeing less than 8 segments is okay, as long as there is only a single double colon. If you see a double colon twice, that's wrong. And then also be aware of your hexadecimal characters, which I'm going to show you towards the end of this video. Now, IPv6 communications. With IPv4, we have something called a unicast, which if we had 4 devices, and it's just a one-to-one conversation between the red and the orange block, that's a unicast. Then we have a multicast, where we can target a group of devices, like the red block is talking only to blue blocks. And then we get a broadcast, where the red block can send a message to everybody who is prepared to receive and listen to the message. With IP version 6, it's very similar actually. We have a unicast, just like with IPv4. Obviously the addresses will be IPv6 addresses though. Then we have multicasting, just like with IPv4, where you can target a selected group of devices. And just like with IPv4, a specific range of IPv6 addresses will be used. The difference comes in here. IPv6 has something called an anycast instead of a broadcast. So what happens with an anycast is a message goes out to anybody who can receive it, but the message will include details about what is the request for, and only a device that can actually answer will actually answer. Now this is slightly different to the broadcast, as with a broadcast you normally have to process layer 1, layer 2, layer 3 of the OSI model, and maybe at the transport layer, maybe you can work out this traffic is not meant for you. But otherwise it's going to be application layer, where you realize, oh, I can't do anything with this. So you spent quite a bit of time as a network card processing this packet to realize, oh, this isn't for me. Whereas the anycast does that notification at OSI layer 3, or the network layer of TCP IP, which means you don't waste time doing transport processing or application processing that you don't need to do. So that is more or less how an anycast works. Now the next thing you want to be comfortable with is the IPv6 mask, which is sort of like the subnet mask for IPv4. The correct name is actually an IPv6 prefix, and it'll usually be written in something called CIDR notation. CIDR or CIDR is shorthand for classless interdomain routing, and it's just a way of writing the subnet mask, or in this case the IPv6 prefix / mask, in a much shorter format. It's usually / and a number. That number is used to represent the number of binary bits that are in the subnet mask. This is something that's more important for you to learn about when you're doing Network Plus, so don't lose too much sleep over it for now. But if the mask is not specified, we assume a /64. So if this long rectangle is representing an IPv6 address, and the mask is a /64, or not mentioned at all, we assume it's an exact 50-50 split, where the first half of the address represents the network prefix, which is the IPv6 name for the network address term that we used with IPv4 in the previous video. And then the second half of the address is called the interface ID, which fundamentally is the same idea as the host address portion from IP version 4. And similar to IP version 4, the mask's length can be adjusted. If you make the mask shorter, that means more of the address is available for interface IDs, which means you can have really large networks in terms of the number of hosts in them, at the cost of having fewer networks. Conversely, if you make the mask longer, that means you get more IPv6 networks at the cost of the number of nodes in the network, which is not that bad considering how big the IPv6 address space is and therefore how big the networks effectively are going to be. Now, the next thing you want to know about are a couple of the important IPv6 network addresses. So first up, that / numbers that you see at the end of these network addresses are the CIDR notations or the masks used by IPv6. So if an address is all zeros, it could be written as : : so 32 hexadecimal zeros with colons separating them, and all 128 bits are defined as a specific address, hence the /128. The IP version 6 name for this is unspecified. It is the equivalent of the 0.0.0 address I mentioned in the IP version 4 video. Acts as a default route. Then you get : 1. So all but the last digit are hexadecimal zeros. The last one is a 1. That is the one and only loopback address for IP version 6. : 2, not a loopback address. Kind of funny. In IP version 4, where we've got 4.3 billion addresses, we set aside 16 million odd so that we can talk to ourselves. Yet in IP version 6, where we have 340 trillion addresses, we only set aside 1 to talk to ourselves. Kind of funny. Well, I did say lessons were learned, didn't I? Then, the next address of interest to you is the 2000 series of addresses, which is called the Global Unicast Range. This is the IP version 6 equivalent of public or internet routable addresses. With the exception of the 2001 0DB8 network. That one was reserved for documentation and examples, so that we can demonstrate stuff safely without messing with the internet. Now, if you're wondering, hang on, we didn't have documentation or example networks in version 4. Well, we used to. 192.0.2.0, 198.51.100.0, and 203.0.113.0 were IP version 4's example networks. But as the address bases have been getting used up, those networks have started to become available for public routing. Then you get FD00. That is called the unique local address or site local address. This is an idea where you could do internal routing within an organization. And if you allocate those addresses, it allows for private internal routing but never crossing over to the internet. Then you get FE80, which is the link local unicast range. That is for local LAN communications where you don't plan to talk to somebody that's on the other side of a router. You're both on the same LAN segment. So between the unique local addresses and the link local addresses, that is effectively IP version 6's equivalent of private IP addresses. And then you get FF00, which is the multicast range for IP version 6. And if you have FF02, that is for link local multicasting, which is multicasting within the local LAN segment, similar to how we had the link local unicast address. But together they basically do the same thing that the Class D addresses do in IP version 4. Now, if you can remember some of those addresses, that'll make your life a little bit easier. Obviously, I have written them with the shorthand, which keeps it a bit more compact. You might see the addresses a bit longer when you're doing the exam, but I did tell you how to condense, and obviously now you can also expand the addresses if you need to. Now, part of the challenge with going to IP version 6 is allocating addresses to your clients. You can go and statically assign the addresses, where you basically go to each device and manually set up its IP version 6 address, its mask, its gateway, maybe a DNS server or two to resolve names. Nothing too difficult there. Very similar to what you could do for IP version 4. Alternatively, you can use DHCP version 6. I know we haven't done DHCP yet, we're going to do it in an upcoming video, but IP version 6 does have its own form of DHCP, which allows a server to allocate an IP address and all the other information to a client that is requesting. And just to impress the people who've done Network Plus with your A+ knowledge, there's something called SLAC, or Stateless Address Auto Configuration, which is where an IPv6 client can, for the most part, self-configure an IP address, mask, and default gateway. Extra information like the address of a DNS server, which we will also talk about in a later video, will need to be configured manually. Now, I just want to get you a bit familiar with the hexadecimal numbering system as well. That way, if they ask you to recognize something that is not an IPv6 address in the exam, they don't trick you with the symbols. So here's a little conversion table for you. And this column here shows you the hexadecimal values. The numbering system has 16 values in total, starting at 0, going up to 9, as you and I would recognize it. And then we have A, B, C, D, E, F. Letters. Now, part of the problem we have as human beings when we're looking at hexadecimal is we're seeing letters and numbers. Don't see them as letters or numbers, see them as symbols. Those 10 values represent those 4-bit binary strings. Those 6 values represent those binary strings. So instead of having to go and do some crazy binary to decimal calculations, it's a simple set of substitution. If you see a hexadecimal value of 2, you substitute in 0010. If you see a hexadecimal value of B, you substitute in 1011. Now for the A+ exam, what I would do is look for anything that is not the letters A, B, C, D, E, and F. If you see any other letter from the alphabet, that is not part of the hexadecimal numbering system and therefore would be invalid for an IP version 6 address. Now, if you want to stop watching the video here, that should be enough for you to recognize it. But if you're curious, how does this conversion look? Let me show you something that I show in the Network Plus series. So if you have your conversion table written over here with just the binary and the hexadecimal values, and you take an IPv6 address such as this one, 2001:0db8, so on and so forth, it's the same one as earlier. What you can then do is start substituting in the 4-bit binary values for the hex values. So for instance, if you see 2001, you substitute in 0010 for the 2, 4 zeros for the 0, 4 zeros again for the second 0 in that first field, and 0001, colon is just colon, so we can put a colon in there. Then 4 zeros for the first value of the second field, 1101 for D, 1011 for B, and 1000 for 8. Colon is just colon, and you could keep rinsing and repeating over and over again. But you are not expected to memorize or know how to do this for A+. This is at most a Network Plus concept. And even then, at Network Plus, you might not get that much about IP version 6, as a significant portion of the world is still using IP version 4. But that should do it for an intro to IPv6 for your A+. What we're doing is we're trying to make people a little bit less scared of IP version 6 at a technical level, so that we can try and migrate the world over to IPv6 at some point. Because with the limited address space that IP version 4 has for us, and the way internet technologies keep growing with things like cellular devices and smart devices, cloud computing, social media, etc., all of these internet-based technologies require us to have more and more addresses, more and more data centers, and we just need more addresses in the address space at the end of the day. So IP version 6 is inevitable. The only question is when. So this is CompTIA, me, and the rest of the industry trying to help you be a little bit more comfortable with it so that we can actually move over. Nonetheless though, I'd like to say thank you for watching. I really do appreciate it. And if you have any friends or family members, colleagues, peers, etc., who would also like to learn the CompTIA A+ series, please don't be afraid to share this with them. Otherwise though, I'll catch you in the next video.